all safe where you are. I'm sharing my screen right now. Can you see it?
Yeah.
All right, wonderful. And welcome to an Astronight. It's the best way of actually spending a Friday evening. As Tom mentioned, I am the Executive Director of the American Association of Variable Star Observers. And what I would like to do today is give you an introduction on those variable stars. What are they? Why should we care? And why should we keep observing them? And I would actually like to start by a very short introduction of the American Association of Variable Star Observers that was actually formed in Cambridge, Massachusetts in 1911, more than 100 years ago. And it was formed as an association to actually do citizen science. It was formed in order to connect amateur and professional astronomers for scientific projects. So since then, we became a truly international organization. We have members and observers from all over the world. We are a very diverse community, which translates to serving people with different needs, different priorities, different professional preparation, habits, cultural background, and they're all unified under the international umbrella of astronomy. We have individuals who are interested in using variable star data for their research projects. We have individuals who are using data with their students in the classroom or outside for different projects. We are working with a very dedicated group of volunteers, and also we are working with our observers, those who acquire data through the telescopes, CCDs, DSLR cameras, and they share the information with a wider community through the AVSO International Database. So this is an opportunity for me to show you some pictures of some of my best friends within the AVSO. Some of them are observers, and here they're with the telescopes. Actually, Christine Larsen, one of our past president, and here is with her solar telescope. She's a solar observer. We have students who come to our meetings to present their work or write manuscripts for our journal. We have all kinds of colleagues who come and give presentations. They present their projects, but most importantly, they collaborate and they work with members of our community on different projects of their interest. So when I was preparing this presentation, I was trying to figure out when was the first time that a variable star was mentioned. It was mentioned in our history, in our modern history, let's say. And I found this very interesting manuscript that says that in the Cairo calendar, 3,000 years ago, ancient Egyptians mentioned a star called Algol that is actually changing with time. Its brightness is changing with time, and it's changing in a very periodic manner. And not only that, the period of this change is 2.850 days. So 3,000 years ago, ancient Egyptians knew that there was a star that shows variability in the night sky. Its brightness is changing, and that it has a very periodic change of its brightness. And they even mentioned this brightness change. Keep that in mind. It's really, really impressive. But before I start telling you all about variable stars and why they're important, why should we care, and how do we measure them, et cetera, let's try the net. Let's play a game. Who likes games? I cannot see you, but I'm assuming that everybody likes games. And for the sake of this game, I would like you all to go to your chat because I would like to talk to you somehow. Or you can just unmute yourself and we can talk this way. And here's the game. And these are the rules of the game. Say that this square is a part of the sky, a night sky that you can see from Texas. And each dot you see there represents a star. Larger dots are brighter stars, smaller dots are fainter stars. And I want to find a way of characterizing how bright each star is. But because I make the rules of the game, I'm going to do things a little bit backwards. So what I'm going to do is I'm going to assign the smaller number to my brightest star to characterize its brightness. So for example, this star that is the brightest in this part of the sky, it's characterized by number 51. This star by number 61, this one 64, 75, 85, and the faintest star in my sky has a larger number, number 91. Yes? This is where you should all say, yay, we got it. So you see a star here that does not have a number assigned to it. And I'm going to name this star Jane because Jane is an awesome name for a star. So if I ask you to tell me, with respect to the rest of the stars in that part of the sky, what number you would assign to Jane, what number would you give her? You can actually start typing. I see a 62, 62,
5.
65, 59. So the way that we're thinking about it is Jane brighter than 51, brighter or fainter than 51? Unmute yourself, just shout.
Fainter.
It is fainter.
Fainter than 50.
How about 61? Brighter or fainter?
Fainter.
Fainter.
How about 85? Brighter or fainter?
Brighter.
How about
Brighter.
75? Brighter. So yeah. So how about 64?
Fainter.
Fainter than 64?
Brighter than 64.
A little bit brighter than 64. So would say that it's somewhere in between 64 and 61, right? 62, 63 is a really good assumption. That is the brightness of Jane on the 10th of June. So I go out a week later and here's my stars again, and everything stayed the same, but Jane. How bright is Jane tonight?
She's close.
Again, the same thing. Is it brighter or fainter than 51?
She's fainter.
It's more
now.
faint.
She's like
How about
91.
61? Brighter or fainter than 61?
Fainter.
How about 64? Brighter or fainter?
It's fainter.
How about 75?
Fainter.
How about 91?
About the same.
About the same.
Yeah, more or less it's about the same that 61. So you saw what we're doing, right? We're comparing the brightness of Jane with the stars around it that are not changing and trying to figure out how bright it is or how faint it is with respect to that. Here's another night of measurements. Same stars field, same stars, same game, same deal. Here's Jane. How bright is Jane tonight?
She's a little brighter now.
Brighter than that. So how about, is it as bright as 51?
No.
Brighter, fainter?
Brighter or fainter, sorry.
Fainter.
How about 91? Is it brighter or fainter?
Brighter.
It's brighter. How about 85?
Brighter.
How about 75?
About this.
Then
75 is brighter, it looks like.
Brighter.
Yeah.
My
How about
probably
64?
Close to 64 and 75.
Yeah, you're pretty much, all of you are right. Really, this is a visual estimate. So Jane is a variable star in the sense that every time we go out to observe it, its brightness is changing with respect to stars that is close to it, whose brightness is not changing. And by the way, what we just did was to build a light curve. Congratulations, you just did your first variable star measurement.
Yes.
So a light curve is the tool that we as astronomers are using in order to assess variability of stars, tell that they're changing with time. And we're doing exactly what we did in that game. We are plotting in a graph the brightness change of a star with time as we actually see it and compare it with other stars in the vicinity. Here's another example of a variable star light curve. It's light curve of light, right? This is the variable star, and this is a star whose brightness is not changing with time. So it's a comparative science. As long as I tell you that, this is a star that is probably variable, and here are stars that you can compare it with in order to assess how it's changing with time. You can actually do this business with your binoculars. You can do them with your DSLR camera, just looking through the eyepiece of your telescope, or even using much more sophisticated telescopes or digital means, such as CCD cameras, CMOS cameras, etc. Actually, here's one of my favorite examples that images of what we call a globular star cluster. It's a family of stars that were born together. This is the center of a cluster. There's thousands of stars in here, packed very close together. And this is a little movie that was created from 4 different images. that were actually taken the one after the other. So you just take picture after picture after picture with something that's a little bit more sophisticated than the camera that you have on your cell phone. And you just put them together in a movie. So if you look at the picture, nothing really moves, really looks really pretty. But if you pay very, very close attention, can you spot things that blink? How about this one? Or this one? Or this one? Playing a different sort of game, discover the variables. I hope that the answer is yes, and I hope that you're nodding your head somewhere saying that, yeah, there are lots of variable stars in there, stars whose brightness is changing with respect to other stars. But what this demonstrates is two things. First, variable stars very easily. And second, we can actually detect variability within the same night of observations if we take picture after picture after picture of the same part of the night sky. So things are changing really, really quickly, especially when it comes to certain types of variables. So moving on, there are different groups of variable stars and classes and types and subtypes and subcategories, just a lot of stuff. But all those things are really boring. So what I'm going to do today and just for you, is reclassify them. And I'm going to talk about variable stars as the good, the bad, and the explosive. Just three categories: good, bad, and explosive. And from there on, we're going to discuss properties like that. So let's start with the good ones. Now, the good ones is what we call periodic variables. These are stars that are doing something repetitively. These are variables that seems to change in brightness with a very consistent way. They do the same thing again and again, and you can actually predict their behavior before you observe it and go out and observe it and actually confirm this kind of behavior. So here, these are two of the most common ways of this kind of variability. These are binary stars and pulsating variables. And I would like to start with binary star system. Now, binary stars are two stars that are tied together by gravity, so they cannot escape. So they're just moving together. And all they do is dance around each other in a very repetitive way. So they move around their common center of mass. Actually, about half of the stars in our galaxy are considered to be belonging in systems like that, binary star systems. And this is a cartoon that shows this dance of the two stars around each other. They can't escape, they're tied by gravity. Gravitational force is really very strong. Here's actually a real life example of what we call a visual binary, where we can see both stars. And actually, if we wait long enough, we can see them moving around each other with time. This is Sirius, the brightest star in Canis Major, the big dog. And it consists of two components, Sirius A and Sirius B. Sirius A is a really bright star that is a little bit more massive than the sun. But Sirius B is a very special type of star. It's what we call a white dwarf. Now, a white dwarf is a star that is as massive as our sun, but it has the size of the Earth. So all that mass is squeezed down to the size of the Earth. So you can imagine this is a really very dense object, and it's also very, very hot. So if you take a picture in visible light, in the light that our eyes are very sensitive to, Sirius A is much, much brighter than Sirius B. However, if you take a picture in X-rays, where really hot objects emit most of their light, Sirius B completely outshines Sirius A. Sirius B is really much brighter than Sirius A. The cool thing with this system is that its periods, orbital period, the time that takes for these two stars to dance around each other once, is only 50 years, 50. What that means is that if you go out and take a look at Sirius A and B in a specific configuration and go back in 50 years from now, you can actually see both stellar components coming back to the same position in 50 years. And we don't get to see things like that very often in astronomy. So if you ever have the chance to monitor Sirius A and B's dance around the common center of mass within that 50-year period, of the times we know that a star is a binary star system when the orientation, the inclination of the two systems, just so that it's like a geometric effect. one of the two stellar components is actually going in front or behind its companion. So it's covering it. What that does is that part of the light of the system is dropping from time to time as one of the stars covering another. And this is actually a cartoon demonstrating this phenomena. This is a light curve, brightness change with time. And this shows that as the two stars are dancing around each other, when one of the two stars are going in front here or behind its companion, the light, the collective light of both stars is dropping in a very characteristic manner. This is just showcasing snapshots of this particular movie, just to show you that these are very deep drops in brightness that are very characteristic for us who are observing these kind of stars, and to tell us that this is a binary star system. Just by looking at this light curve, we can tell that there are two stars together. Remember, we cannot resolve the two stellar components. Everything that we do, even with the most powerful telescope from the Earth, all that we see is a little dot. So by taking data after data and plotting a light curve for this kind of dot, we can tell that actually it's not one star, it's two stars that are dancing around the center of mass of their system. Actually, Algol, remember that star that was included in the Cairo calendar? Algol is actually an eclipse binary system. And it's really impressive that ancient Egyptians knew how to measure the period of this particular binary and assess that one star is dancing around each other with a period of 2.8 days. And what is even more impressive is that the same technique that the ancient Egyptians used in order to study eclipsing binaries, the same technique we are using to study eclipsing binaries, is now being used to study exoplanets. I'm pretty sure that somewhere, somehow, you've heard about the exoplanet transit method. What the exoplanet transit method is in principle is that you have a star and you have a tiny little planet around that star. And when the planet is actually going in front of the star, then the brightness of the system, the total brightness, is dropping just a little bit. So it's pretty much an eclipse. It's exactly the same thing as in eclipsing binaries like that. The only difference is that instead of talking about two stars, we're talking about a star and a planet. And actually the effect, the depth of the eclipse depends on the size of the planet. So here's a cartoon that showcases a star, say as bright as the sun, in three different configurations. Here is when there is a Jupiter-sized planet that is passing in front of it. And here you can see the blue light curve, how the light is being cut. So you can see a little eclipse while the Jupiter planet, size planets is passing in front of the star. The green square is showing you a Neptune-sized planet, and you can see the smaller eclipse that this particular effect has on the light of the system. So it's a little bit drop. And you have to believe me here when I tell you that there is an Earth-sized planet, so small that we can't really see it with our eyes, even in the little cartoon here. And the red little line here showcase the effect on the light curve, the total brightness of the system. And you have to believe me in that. There is no effect, none whatsoever. And that is why, in order to detect Earth-sized planets around stars, we really need to go to the highest accuracy, highest precision. We can measure this kind of transits. We have to go to space. And that's why we have all those space telescopes trying to detect these Earth-sized planets. So the same technique that ancient Egyptians used in order to study Algol is now being used to study exoplanets. I find this amazing, really amazing. So the second type, excuse me, the second type of periodic variables, I would like to discuss what we call pulsating variables. And these are single stars. These are not two components, just one star, but they're going through a very special phase in their life, a very special time in their life. So let me take a step back here. Stars are huge balls of gas, really big gas balls. And those gas balls are controlled by two main forces. there's a force of gravity that is trying to squeeze everything together as densely as they can. So if you leave gravity to do its thing, everything will come together and they will crash with each other and just keep crashing, keep crashing. But at the same time, at the very center of a star, there's a nuclear reactor that is converting hydrogen to other elements. And as a result of this nuclear reaction, just imagine a heater. It's like a space heater, for example, but much, much, much more powerful. There's radiation that is emitted outwards. So there's heat that comes outwards. And heat is trying to actually push everything apart, like pull it apart, just completely destroy the star. So you have gravity pushing, you have radiation pulling, and at some point, these two forces come in some kind of balance, what we call in science, hydrostatic equilibrium. There's just in a steady state where the star is just sitting there and it's hanging out in space and no one's winning. No gravity, no radiation pressure. So this is a very nice little movie that ESA has created showcasing this event. So here's our friend, the star, that is actually hanging out a big gas ball. Gravity is balancing gas pressure and it's just there. But at some point, hydrogen at the very center of the star finishes. It's not infinite. And this equilibrium is being disrupted. And then a battle, a real war starts between gravity and gas pressure trying to dominate each other. When gravity wins, the gas is compressed. When gas pressure wins, the gas layers are pulled apart. And this is actually continued for a while until the star moves in the next phase of its life. But until it does that, then the star expands and contracts. So in a very characteristic manner. It literally, let me play this again. I really like this movie. It literally changes its size. So here's again our star in hydrostatic equilibrium state. And then no more equilibrium. Come on, little star, you can do it. And now you see the star expanding and then contracting. Then again. And then contracting again. So you have one huge star going out and in, pulsating, changing its size in a very periodic manner. So pretty much this is a very, an artist's conception of this kind of expansion and contraction. But however, if we observe this star here from the Earth, we will see that its brightness is changing in a very characteristic manner. Its brightness is increasing and decreasing with time. And if we actually build a light curve of brightness change with time, we actually see this characteristic shape that tells us that this is a single star and it's pulsating. So just by looking at the shape of the light curve, we can tell the nature of this particular star. Why are these important? Let me tell you a short story of that extraordinary young woman who worked at Harvard in 1911. This woman actually used photographic plates, a very old now technique to capture the light of stars. So it was these big glass flat plates that had information on different stars. And she was measuring brightnesses of stars just from these plates. Very, very painful, back more than a century ago, actually. Doing it by hand, no computers, no electronic means, just one by one. And she was working on a whole bunch of data from this tiny little fuzzy thing. This is the Small Magellanic Cloud. This is a satellite, a nearby galaxy, a satellite galaxy of our own. So it's a different galaxy that is relatively far away. So she had a whole bunch of data on this little galaxy. And while she was actually working on her data, try to classify stars and put them in categories and see how bright they are and measure their brightness from plate to plate to plate, she started discovering lots of periodic variables called Cepheids. This is a very characteristic type of variable star that's increasing and decreasing with time. But what she was really very impressed that she actually found a lot of them, tons of them. And not only that, after measuring the periods of the Cepheids and the relative brightness of each one, she found a relationship between the period and the brightness for all these stars. And actually, she found that stars with longer periods were brighter than stars with shorter periods. This actually helped her build what we call a period luminosity relationship, a relationship between the intrinsic brightness of those stars and their periodicity. And that helped her determine the distance to the Small Magellanic Cloud. Why is that important? Or how do we measure distances in the universe? What is our yardstick? Can we actually take one side of a yardstick and give the other one to someone else and they go to a nearby star and just measure the distance, and we know that it's like something is 300,000 miles away from here? How do we know it? Well, it's really very difficult. It's not straightforward. And this method, the Henrietta Leavitt developed, helped us measure distances in nearby galaxies. So by studying those stars, even now, astronomers are determining distances to nearby galaxies. So it's really very important to measure their periods, to discover more, to build Henrietta's relationship for all those stars, and actually keep measuring them as accurately as possible in order to actually determine those distances even more accurately. So enough with the good variables. Let's go to the bad ones. The bad ones. All right, and I'm going to show you the prototype of those stars. And I would like you to go to the chat and write down which one it is. Do you recognize this star? Or unmute yourselves and tell me which one it is. Looks familiar?
The sun.
The sun.
Yes, thank you. This is our own star, the sun. So this, I would say, is the prototype of this category. It's a star that we knew was offering a lot of heat and a lot of energy to us, but the first person who studied this particular star in details through a telescope was Galileo about 400 years ago. And actually, legend tells us that what Galileo did was he took a piece of glass, like the one that you have on your windows, and he put it on top of fire, and he collected a lot of smoke on the glass. So the glass was kind of blackened. And he took this kind of glass and he put it in front of his telescope to look at the sun because it was really very bright. Well, Galileo died blind. Should I say it again? Blind, blind, blind. He completely destroyed his vision. That was the worst thing he could do for himself. We know now that you're not supposed to look directly at the sun, especially through a telescope or binoculars, without having a special filter. And that filter is not your sunglasses. That filter is not your x-rays. That filter is just a very, very, very special piece of plastic that actually allows you to look at the sun safely. So if not anything else, the one thing that you're going to take away from this presentation, that you're not supposed to look at the sun directly. Please don't do that. However, Galileo was the first one to leave us with a very rich record of the sun's surface, the sun's outer atmosphere. And what he said for the first time is that the sun is not a perfect object. It's not a perfect sphere. It has little inhomogeneities around it. It has these black little dots on it. And not only that, if you look at the sun from day to day, you will see these dots moving. And they're moving as if they're stuck on the sun, just rotate with it. This is a part of Galileo's log, actually showcasing those little spots that we now call sunspots. We do know that the sun actually, not only it's not a very quiet, smooth ball, but we know that the sun is a very, very active, a very energetic object. These are some, and actually since the sun is the nearest star to us, we have the capacity to study it in detail. This is the only star that we can actually take these kind of pictures. These are real pictures, right? From the Earth or from space telescopes. So now we know that these are sunspots. These are the little spots that Galileo was sketching. So we know that the sun has spots and it has flares and it has prominences and filaments and coronal mass ejections and all kinds of activity going on in it. It's a very, very hot and very energetic ball of gas. And all of them are due to the sun's magnetic field. So apart from the north and the south magnetic pole of the sun has tiny little dipoles all the way everywhere in its atmosphere, everywhere. And that is what causes material kind of going up and down those dipoles like a roller coaster. So material goes up and down, creating these big loops. So when you see something like this, like a nice big loop on the solar surface or outer atmosphere, then it is because of the magnetic field of the sun, one of these little magnetic loops. And actually, in this particular example, one of those magnetic loops is breaking and it's throwing material most of the times towards us in what we call a flare. We now know that there are stars, that other stars have flares as well. This kind of energetic ejection, like throwing material, lots of gas and lots of fire towards us in principle. And then the reason why we know that is because we have observed them. And guess what we've done? We have taken light curves. So this is a star that is nearby. It's called UV Ceti. It's one of the most active stars that are nearby. And this is a light curve, brightness change with time. And what you see here is that you can see nothing, and then a very, very abrupt increase of the brightness, as if, there's a huge explosion that is declining really slowly as the material is being ejected from the star, and then the star comes back in an equilibrium. Now, I'm going to go back to star spots and tell you something very interesting that we've discovered. We have discovered that as the star rotates, the star spots and sunspots rotate, they come in and out of our line of sight. So they change a little bit the light that we get from this star. It's like you have a big rock that is covering part of the star, but this rock, this dark area is actually disappearing when the star is spinning around its axis. And what we found is that there's a very interesting relationship between how many and how many spots a star has and how big those spots are and how fast it rotates, in that stars that rotate faster have bigger spots. So if you build a light curve of those stars, you will see something like this, like a very characteristic undulation in the light curve as the spots are coming in and out of our line of sight. Want to hear something even more interesting? We also found that there is a correlation between the number of spots that a star has, how fast it rotates, and how old it is, in the sense that younger stars have more and bigger spots and they spin much faster around the axis. And this way, astronomers have actually determined a relationship between the age of those stars, how many spots they have and how big they are and how fast they rotate. It's what we call age-activity rotation relationship. Why is that important? Well, stars don't come with birth certificates. How do we know how old stars are? Have you ever wondered? How do we know how old our sun is? How do we know how old stars are in the field? So one way of finding out is actually observing those stars, taking light curves, brightness change with time, and actually see how fast they spin, how big their spots are. And from that, there is a relationship that gives you their age. It's really cool stuff here, right? These are practical applications of observing this type of variable stars that I really, really like. So with that, I would like to segue to some of my favorite ones. The explosive, the bad dudettes and dudes. And I'm gonna introduce only one types of those, what we call cataclysmic variable. Now, here's the deal. This is kind of a complex system in the sense that it's a binary star system. Remember what we said about binaries? There are two stars that are dancing around the common center of mass. They're just tied by gravity. They're not going anywhere. And they're just dancing around them. Now, one of them is a star that has mass, say, half of the mass of the sun, more or less, maybe, in this particular example. The other one is a white dwarf. these tiny little ones, a white dwarf. Remember what we said about a white dwarf? It's a star that has a mass of the Earth that is squeezed all the way down to the side, the mass of the sun squeezed down to the size of the Earth. It's a very dense star, extremely dense, extremely hot. So if you put those things together, then the little white dwarf will start eating its companions, will start cannibalizing its companion. So material will go from one star to another. And actually, this is the best example I can tell you. This is exactly what's happening. This is your white dwarf, and this is the companion star. And the companion star is being eaten by the white dwarf. Now, here's what's happening in these cases. These two stars are moving around their common center of mass really fast. So we're talking about an orbital period, a period less than 10 hours. That's fast. You think how long it takes for the Earth to go around the sun? We know that, right? 365 days and some change, a year, right? And if those two stars are spinning around each other, dancing around each other with a period of 10 hours, then material from one star to another cannot go straight to the other one. So what happens here is as they spin around, material from the Loma star, as it's being cannibalized by its white dwarf companion, is forming a siphon, some kind of a whirlpool, as it actually moves in a disc-like construction towards the white dwarf. So pretty much the complexity of this system is that you have the two stars, this one and these tiny little one, and dense one, a very hot one, is eating its companion, and it's eating it through a whirlpool-like accretion disk. That's what we call an accretion disk. So what's happening here is something very similar to what's happening to us when we eat. Sometimes when we eat fast, what do? We burp. So there are burps or bursts that are very characteristic in these particular types of stars. And they are called outbursts. And we can see that, and they're because of inhomogeneities of how one star is eating the other. And we can see them in the light curve. So again, that this is brightness change with time. And pretty much these are the two stars, one is eating the other, and then the star burps and goes all the way up. So the brightness of the system as a result of a burp is actually increasing. Now, I want you to unmute yourselves and tell me what happens when you eat too fast.
You burp.
Up.
To say that you eat too much too fast.
You throw up.
Yes, you do throw. Those stars do throw up. So from time to time, when the white dwarf eats a lot of food, very, 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 very quickly, it doesn't have time to digest it. So what happens is that it forms like a blanket of material outside. It keeps eating, right? And it can't handle it anymore. And when it can't handle it anymore, it throws up. So by that, it ejects its outer layers in what we call a nova eruption. So a nova is a white dwarf that actually has a really bad misdigestion. So it cannot digest its food from its companion. This is a cartoon that showcases this particular type of effect. And this is actually a real picture from the Hubble Space Telescope from a nova that went off in 1992. You cannot see the two stars. They're buried somewhere in this hot mess in the middle. But what you can see is that the eruption happened. It formed, in principle, a bubble of material, but because of other effects, it looks like one star throwing up that is going in the interstellar medium and actually gets in other stars as well. Now, some of those stars, like humans, never learn. So they start eating a lot of food, like a lot of food, again and again and again, and they throw up again and again and again. And this is what we call recurrent novae. Novae, stars that have shown more than one nova eruption. In this particular case, ignore this star. This is nothing. This is a nova, and the two components are somewhere buried in the middle of the little bright dot. But what you see here is material that has been ejected from the binary because the white dwarf keeps throwing up again and again and again. But you know, there are some cases where the white dwarf does not throw up its material and actually has time to process material and digest it. And what happens in that case? What happens when you eat a lot of food and you don't throw up? You gain weight, don't you? That's what happens with the white dwarf. It starts increasing in mass. And as a result, at some point, when the white dwarf reaches a very specific mass, it triggers a massive explosion in its interior that completely destroys the star, ejecting really large amounts of material in the interstellar medium. And this is what we call a supernova. So these little movie showcases that, you know, the white dwarf eats its companion. At some point, it can't handle it and it completely bursts, it dies. So this is what happens in nature. Supernovae, I'm pretty sure you've heard about supernovae, are some of the most dramatic explosions in the universe. They're like fireworks in the universe. And they're extremely bright. And that is one of the reasons why we really like observing them. They're really bright. We can see them in galaxies far, far away. This is a beautiful spiral galaxy that is really far from here. You can see the spiral arms and nice dust lanes here. At the center, most likely there is a black hole. And this bright dot at the edge is a supernova of the type that I just described to you, a white dwarf that had a bad digestion. It ate a lot of food and it completely destroyed itself. It bursted out. Actually, the nice thing with supernova of that type is that we can see them everywhere in the universe. They don't depend on the type of the galaxy. They don't depend on whether a galaxy is a spiral, has a nice structure like this, or it's an elliptical, so it's much more smooth in structure. So these are two more examples, excuse me, of this particular event. This is actually M101, one of the very favorite galaxies for stargazers. So if you ever have a chance to look at this galaxy through a telescope, you'll really be impressed. I really love it myself. This is the center of the galaxy. You can see its spiral arms. And this bright dot here is a supernova like the one that we discussed before. Here's an elliptical galaxy. This is in different wavelength. This is an X-ray. But you know, this is a supernova here. And here, this is the center of the galaxy. So the supernova eruption can outshine the galaxy itself, the center of the galaxy. You can see it really, really deep in the universe, very, very far, far away from us. Now, when you build a light curve of those events, because they all come as a result of a white dwarf reaching a specific mass before it erupts, we expect all those events, all those light curves to be more or less the same, and they are. This is a light curve, like a composite light curve, collection of light curves of this kind of events. So each dot is a different supernova. So if you follow the blue dots and the red dots and the orange dots and the yellow dots, they all fall on the same curve. And that is one of the cool things about this kind of supernova. That's one of the things that make them very unique. They look the same no matter where we see them in the universe. And this is another characteristic. This is what we call a spectrum. We took this kind of data by actually looking through instruments that are like prisms. They analyze light in all the colors, and we stretch those colors as much as we can in order to identify different chemical elements. And one of the things that we see in these types of supernovae is that they do not have hydrogen. That is another way of us telling that this bright, bright, bright dot in the middle of a galaxy like this, for example, is a supernova of the type that I just described to you. But you know something? The cool thing with this characteristic is it makes those particular supernovae what we call standard candles in the universe. Standard candle is something that has that's the same properties no matter where you look at them. So if it looks like this or like this in a galaxy that is nearby, it looks the same in a galaxy very far away. So the light curves and the spectra of the supernovae look the same, whether we're looking at an event in a nearby galaxy or in our own galaxy or in a galaxy that is really far away in the universe. Why is that important? Well, if we know what is the absolute magnitude, and don't worry what exactly that means, but if we know the absolute magnitude of all those events, and we do know them, it's the same, We know that it's the same. And we measure the brightness of the event. Then, and we can do a little bit of corrections because of the dust that exists between us and the event. Then we can literally plug those values in this little equation and measure the distance to the event. So by measuring the distance to that supernova, we know the distance of its host galaxy. And this is another way of measuring distances in the universe. This is how we know some of the most far away objects in the universe, how far away they are. And this is why observers, astronomers now, still care to measure this kind of events, and they're really hunting them. They try to figure out how far in the universe they can look, how far they can measure distances in the universe using those events. Not only that, but by measuring those particular light curves and measuring spectra of these particular stars for the first time, not too long ago, astronomers managed to actually figure out the fate of the universe. What's going to happen to the universe? They know now that the universe is expanding, so it's growing. Not only it's growing, but its speed, its velocity is increasing with time. It's accelerating. And there's this magic thing that is called dark energy that is driving this acceleration, is responsible for this acceleration. And this, my friends, this result that was derived for the first time for distant supernovae was the reason why two groups of astrophysicists in 2011 got the Nobel Prize in Physics for their work of discovering the accelerating expansion of the universe through observations of distant supernovae. So it's such a cool result. It's a really cool research line to follow, and it's very active research right now as well. But you know, these are not the more energetic phenomena in the universe. These are what we call gamma ray bursters. These are the the collision between two neutron stars or two black holes and a neutron star and a black hole. And we can see them very a set of digital images that were taken the same night, one after the other, like the ones that I showed you of the cluster. And you can see one of those eruptions, one of these gamma ray bursters that is going off. You can't even see the host galaxy here. It's too faint to see it, but you can see this event. And these are actually, some of these are progenitors of gravitational waves. You've heard about gravitational waves, I hope. And these, again, discovering that some of these are sources of gravitational waves gave a Nobel Prize in Physics in 2017. So, you know, I hope that I gave you a taste of what's happening out there. The universe is a huge, huge place. And the universe is, and exploring the universe is part of who we are. It's part of human nature. You know, we are explorers in nature, and we have explored our own planet. We have figured out most of the beautiful physics of our planet, and we want to understand what is around us, what is outside our planet. And since we can't exactly join the enterprise to actually follow its trajectory far, far away and deep in the universe, and we can't join Starman on his trip through the stars, well, we use our telescopes. That's all we do. We use our telescopes, we use our cameras, we use our imagination, our binoculars, and we measure light curves of variable stars. And by measuring those light curves, we try to understand some of the most energetic, some of the craziest phenomena in the universe. If you want to learn more about variable stars, you can go on our webpage, avso.org. We have a whole bunch of what we call observing sections that has information of all types of variable stars in them. So I would like to invite you all to join the exploration of the universe through light curves, through variable stars, through reading about stellar variability, and help us understand what's happening in the universe. So with that, I'm going to again remind you of our webpage and leave you with my favorite cartoon. This is Calvin and Hobbes. I hope you are familiar with them. And they sit outside and they're looking at the sky. And Calvin says, you know, if people sat outside and looked at the stars each night, I bet they lived a lot differently. You know, astronomy gives us perspective. It shows us how big and small we are in the universe. It shows us how precious our lives are. We live on a very actually tiny little rock around a boring star, and we're going to live for 100 years. So all we can do is actually make the most of it. So I hope that you enjoyed this presentation. I would like to thank you for your attention and ask if there are any questions for me at this point.
Okay, before we take questions, can we all give Stella a round of applause?
Thank you. So let me stop sharing my screen so I can see you all.
Okay.
Ooh.
All right. And now what I'm going to say is if you want to ask a question, if you could please click on the participants button down at the bottom and then click raise hand. And that way we can figure out who has a question.
Or we could use a chat.
Yeah, you could use the chat also if you're shy about speaking to a large audience. Or you could just shout out your question too. All right.
Oh my gosh, we all know everything.
Yeah.
And right now we're going to go and observe variable stars, right? Now.
Okay, yeah, Linka?
Hello. So
Hey.
my question is, okay, there is a question in the chat.
Yeah,
How
we'll take
long
yours
is
first, and then we'll go to
solar
the
day?
question in the chat.
Okay. So my question was, what inspired you to, what inspired you about variable stars to, pursue this field?
They change. I love
They
things that
change,
change.
right.
Yes, I do love that. I love things that change in the night sky. I love things that keep me up at night, and they keep me questioning, and they keep me want more data, and they keep me want to study and understand those stars more. Astronomy is a fantastic, it's an amazing science. It combines science and art. It's because we can't go to the stars now. We can't go and take pictures, real pictures. We can't take a scoop of stars. All we have is light in our hands. We have to be very creative about how we analyze light, how we interpret that light, how we explain what we see. And we actually have to put stars together, data together and work with each other in order to put as much brain power to understand the phenomena that we see. And with that, we create a three-dimensional picture on something that is much, much bigger than anything we've ever experienced and much more energetic. Remember, I talked about pulsating stars. Just imagine a star changing size. It's insane, isn't it?
Right, yeah.
Yeah, it's really cool. And we can actually study those things from the Earth, right? And understand why and how it changes. And with all the layers that are going out and in, because they don't even go out and in the periodic manner. They don't go all together. Some of them are colliding and some of them are, ugh. It's messy, but it's really fun. It's really fun.
Thank you.
Yeah. All right. So I have some questions here on the chat. So what I'm going to do is read and answer as I can. One of them is, how long is a solar day? The average solar day is about 26 days. And yes, you can measure average. And yes, you can measure spots. If you have a solar telescope, remember, a special type of telescope, you can actually take one measurement every day and see spots moving around. Spots have started appearing again. And yes, we have a big group of individuals who are measuring spots here. How fast is the fastest variable star? Oh my gosh. What do you mean by fast? I do not know. I hope I'll go look it up. That's what I'm going to do. I really don't know how fast the fastest star. Can you observe Betelgeuse for Texas Tech telescopes? Oh, absolutely. You can definitely observe Betelgeuse. Actually, we have more than 130 years of data on Betelgeuse here at the AVSO. And actually, you don't even need a telescope. You need a pair of binoculars, and Betelgeuse is a fantastic object to observe and study. We have 130 years of data on Betelgeuse, and last year it did something different. That's why I love variable stars. No matter when you come and say, hey, I understand what's going on. It's one of the brightest stars in the sky. From the 6th brightest star in the sky, it became 21st. And we're still trying to figure out why. But if we didn't have all the data, then we wouldn't be able to see that. It's really, really cool. My daughter would like to know if there are variable stars in the Kuiper belt. So the Kuiper belt is part of our solar system. It's part of our sun's family. It does not consist of stars. It consists of rocks. Just imagine leftovers from when our own sun was formed. So in principle, every star that is out there should have a Kuiper belt itself, a whole bunch of rocks around it. They're just too faint. Other questions? Everybody's trying to digest what I just said.
Maybe if we go back to Lindy's question too,
Yes.
maybe if you could say what you mean by fastest variable star.
And I'm so going to Google that.
Okay, now we have a few more questions in there also.
What do you do when you're not observing the night sky? I like reading, and I have a puppy. I'm playing with him. So I'm actually, my puppy is 7 months old. So I absolutely adore him, but I really like to read. So I really like murder mysteries. I can tell you more another time. Is there a way for us to look at the data for Betelgeuse? Yes, absolutely. Our light curves are all our data, everything we have at the AVSO is open access, open source. So you can take a look at the data. We have ways for visualizing data. We have ways of analyzing data. Hold on. You give me 1 second. I'm going to get a light curve Betelgeuse for you. Real life, real time. Okay. Actually, why am I doing that? I'm going to show you how to do it. Oh, it's not helpful. All right. May I share my screen again? I would assume that's a yes.
Sorry, I think it should be fine.
Yeah, I am. All right.
Yeah.
So this is the AVSO webpage, avso.org. You can find all kinds of stuff in here, all kinds of information. Here, which says star name, I will put Alpha Ori, which is Alpha Orionis is Betelgeuse's name, and then plot a light curve. Click. And then you're going to get our light curve generator. It takes a little while because there's lots of data on Betelgeuse. These are the when in the sun, and these are the most recent data. So let's do the following. Let's move these to calendar dates, and then let's do that. There's a lot of data, my friends, on Betelgeuse. Here we are. So these are data on Betelgeuse from 2001. So we're talking about 20 years of data, more or less. And this is where it is now. So all the black points are visual data, measurements that people took just by looking through binoculars with their eyes. No digital means, no sophisticated equipment, nothing. And you can see that Betelgeuse were doing something, right? It was changing with times. So each block that you see here is 1 year of data. And then Betelgeuse went behind the sun, or actually we moved on the other side of the sun. So we could not see it anymore. So this is what we call seasonal gaps. So it was doing its thing every year. And then last year, it just dropped. And, we're very used to saying, oh, Betelgeuse, it's not doing much. Look at that. It's not doing much. And then suddenly we saw that. Oh my gosh, what's going on with Betelgeuse? So this is what I'm saying that, and then it recovered. This is where it is right now. So what's going to do tomorrow or next year or in 10 years from now? I have no clue, my friends. No clue. But this is what, keeps astronomers happily employed. It's really fun to do astronomy. All right. The fastest variation in light. Pulsars. These are actually little lighthouses. These are very, very dense stars. So remember what we said about, step back. Remember what we said about white dwarfs, that are stars that have the size of the sun, that is squeezed in the size of the Earth. White dwarfs is stars that have the size of the sun, squeezed to the size of Austin in Texas. We're talking about super dense, to the point where we don't really understand how matter is formed and kept together at the center of those stars. There are lots of theories around that. There are lots of very active research. So those stars tend to spin really fast. We're talking about spin period of milliseconds. That actually emits some kind of light through the North and South Pole. Now, if the North and South Pole points towards us, every time, oh, here you are. If the North and South Pole points towards us, every time the star spins, we'll see light emitted towards us. And every time that we see this kind of light being emitted, we see a blip in the light curve in principle, like a really fast blip. So we're talking about milliseconds. Really fast. All right. Are there programs for school kids and general public to contribute data or participate in observing programs? Grab a pair of binoculars. Yes. Yes, the answer is yes. If you want to, you can actually go try outside. We do have, all right. We do have what we call 10-star tutorial. I'm going to write it here. Let me actually find it. And also look up our resources. We're coming up with more information for anyone in principle, no matter what your age is, to look at specific variable stars and provide visual measurements that you can make with your eyes. So what we do with that is we give you a star. We tell you which constellation it is and where it is with respect to really bright stars. And we tell you which stars to compare it with. Remember the game that we played at the very beginning of my presentation? That's all you're doing. That's all you do. You just compare it with different stars. You say, oh, it's closer to this one, or it's closer to that one in brightness. So the 10-star tutorial is actually a beginner's guide on some of the brightest stars in the northern and the southern hemisphere. So you can get started with that. Or if you want help or more information, avso@avso.org. Send us an email. Most of those emails come to me. So I'll be very happy to direct you and help you get started with your own program. Let's see. Can we upload raw data to the AVSO? Can they be just images, and do they have to be light curves? We accept light curves at the AVSO. We don't have the bandwidth. I mean, images are really very big files, they're huge files. So our databases are not large enough to be able to have thousands of images from all over the world. Right now, we have 43 million data points in our database. Just imagine 43 million images. We wouldn't have the capacity to store them. But you're very welcome to actually submit your own data at the AVSO. The dip in the light curve bilge is very surprising to me. What is the most surprising or noteworthy observation in modern astronomy to you? Oh, what a question. That's an awesome question. You know something, every time that I look at a new light curve, or I learn something about a star I didn't know about, I'm surprised, I'm amazed. I can point you to big discoveries like dark matter and structure of galaxies, stellar variability, cataclysmic variables, my favorite stellar cannibals. I love those stars. They change on timescales that I just don't understand. Our sun is one of my favorite stars ever, because it's nearby. We've been studying it for hundreds of years, and we still don't understand it. And it is our prototype for everything, for our solar system, for energy, and for light, and for life. I will go honestly, because it's an awesome star. Am I over my time, Tom?
A little bit, but we can keep going.
I don't want to
Um,
steal time from the next presenter.
I think that's fine. Linka, do you mind?
Absolutely, yeah, absolutely. Please, because I
Yeah.
also have questions too.
Yeah.
Oh yeah, please ask.
Yeah.
All right.
Okay.
The dip,
All right.
yeah, the dip in the lycra Betelgeuse was surprising to everybody. I went to the annual meeting of the American Astronomical Society, 3,000 professional astronomers in the same room this past January when we could still travel, right? About a year ago. And we had a table for the AVSO, and every person who would come to the table would ask me, so what's going on with Betelgeuse? And my response was, I have no idea. I didn't do anything. Just go ask Betelgeuse. It was surprising to all of us. But this is how astronomical discoveries are happening. You think you know something, and then the star is doing something you don't understand. So that's research. And we're still trying to understand it. Still trying to understand it. More questions? No more questions?
Oh, yes, I did have one. So, okay. On behalf of Women in Physics for our department, we always like to ask this question to people who come and speak. And as a woman, how do you feel, or do you have any tips or any advice for students who would want to, of course, follow in your footsteps? Any advice?
Work hard. The one thing that I'm telling people is that, women or men who I meet and are asking for advice. I am not a genius. I was not born with a PhD. I had to really work hard for what I'm doing and get where I am. So in principle, the bottom line is if you work hard and you're diligent with your studies and your research, you can get anywhere you want. You can be as successful in any profession you choose. The sky is not the limit. But at the same time, have friends. Have a life outside your academics. This is something that will enrich your soul and your brain. Play sports, read a book, cook, play with your puppy. I do that. Play music, play computer games, do science experiments, do outreach as well. And something, support each other. You're going to be each other's support group and network. You will find each other again in all paths of lives, and you never know. You just never know. I have friends that I don't see for years and years, and then I see them at completely random places, and it's always wonderful to catch up. Astronomy is a very diverse and very inclusive profession. There are lots of individuals out there who are very willing to help you, advise you, mentor you, and make sure that you're successful. Don't be afraid to reach out to them. Don't be afraid to reach out to your teachers. Don't be afraid to actually ask tough questions. Don't be afraid to ask for advice. That's what they're there for. I'm serious.
Absolutely. Thank you so much.
You're most
Thank
welcome.
you. Appreciate it.
Already causing a problem with observational data. They're planning to launch every 1,000 more satellites. Do I want to get started?